Most electric scooters hitting the streets right now are holding something back. Out of the box, manufacturers deliberately cap their top speed, locking the motor's true potential behind an artificial ceiling. This restriction is not a mechanical limitation. City regulators mandate strict speed limits, and corporate rental fleets like the ones here rely on identical, predictable hardware to comply with local laws. To achieve that standardization, manufacturers throttle the power before the scooter ever leaves the factory. To reclaim that lost power, you have to bypass three distinct layers of restriction. The manufacturer locks the scooter through the dashboard software, the internal firmware, and a physical hardware loop. Breaking through these barriers requires specific tools: a basic screwdriver set, a Bluetooth-enabled smartphone, and a digital multimeter. Modifying these systems is often labeled as hacking, but that is a misconception. We are simply removing the digital and physical roadblocks the manufacturer installed, letting the native hardware run at the capacity it was originally engineered to handle. The easiest layer to clear is the parameter menu, commonly called P settings. This is the primary software gatekeeper, and it is accessible directly from the dashboard interface. To bypass the standard display and enter this hidden menu, ensure the scooter is stationary and press the power and mode buttons simultaneously. Hold them down for exactly 3 seconds. Navigate through the menu until you reach the P8 parameter. On a few specific models, this might be labeled P1. In either case, this value controls the master speed limit. Use the display buttons to max out this number. While you have the menu open, locate parameter P3. This controls the strength of the regenerative braking. Dialing this setting up helps recover kinetic energy to optimize your battery life, which is necessary once you start drawing extra power for higher speeds. Saving these changes will clear superficial dashboard limits and error codes, but for modern, smart scooters, the internal computer will still restrict the current. To unlock the motor, we have to override the digital brain itself. High-end models rely on hard-coded firmware to dictate exactly how much power reaches the motor controller. The dashboard can ask for more speed, but the firmware has the final say and will deny the request. To bypass this, we use a third-party smartphone app connected via Bluetooth. This software intercepts the scooter's factory DOT bin file and replaces it with custom firmware, stripping away the coded restrictions. This exact step carries the highest risk of catastrophic failure. Pushing unverified data to the controller can overload the circuitry and blow the scooter's internal fuse during the data flash. To survive a firmware flash, your board needs a safety net known as the two-fuse rule. Manufacturers realize the vulnerability of single-fuse boards, so most models produced after March 2017 are built with dual fuses. Before you initiate the flash, verify your hardware. Check the side of the scooter's base for a printed serial number, or connect to the official manufacturer app and check the battery production date in the system information screen. Skipping this verification on an older single-fuse model will permanently brick the battery. Digital overrides always carry severe physical risks. For models that do not rely on smart firmware, the restriction is mechanical. The final barrier is a physical speed limiter wire located inside the controller box beneath the deck. This schematic breaks down the internal wiring harness. You will see thick 10 to 14 gauge phase wires that carry high current to the motor. Ignore those. You are looking for a thin wire isolated from the main power lines. Its identifying trait is its shape, a single piece of wire that loops out of the controller casing and plugs right back into the exact same box. Do not cut a wire based solely on its color. Manufacturers frequently change wire colors during production. A digital multimeter is the mandatory verification tool to confirm the wire's function before making any modifications. With the scooter powered on and the battery safely grounded, probe the wire. Confirm a reading between 3.3 and 5 volts. This proves the wire is a low-voltage logic signal, telling the controller to cap the speed. For advanced users chasing extreme acceleration, there is one alternative hardware adjustment, commonly known as the shunt mod. By adding solder to the controller's shunt, the small metallic staple shown here, you reduce electrical resistance, allowing maximum current to flow directly to the motor. By safely severing the verified logic loop or modifying the shunt to handle higher current, the final physical barrier is eliminated. The motor is free to operate at its raw factory output. The scooter is now completely unlocked. But hitting its absolute maximum speed shifts massive new stress onto mechanical components that were originally dealt for casual commuting. This chart maps the underlying physics of your new top speed. While your velocity increases on a linear path, the kinetic energy, and therefore the impact force in a crash, follows an exponentially rising curve. Look at the data points. Doubling your speed from 10 miles per hour to 20 miles per hour does not double the impact force. It quadruples it. This surge in kinetic energy completely overwhelms factory brakes designed for a 15 mile per hour limit. Calipers and rotors cannot dissipate the extreme heat generated at 30 miles per hour, causing brake fade and drastically extending your stopping distance. Unlocking a scooter's speed transforms it into a high-risk vehicle. The manufacturer is no longer capping your power to keep you safe. The ultimate responsibility now rests on you to upgrade your braking hardware, invest in proper safety gear, and calculate stopping distances before opening the throttle.